In the bottom left-hand corner of our sky maps, actually, they have a little scale called magnitude, okay? And this is the one thing that kind of drives me nuts, and you can see it on this slide. Which is brighter, the sun or Pluto? Which is brighter from our sky, the sun or Pluto?
The sun.
The sun. And look, check this out. The sun has like a negative 26-ish with regard to how bright it is. All phones away, please. Thank you. How bright it is, negative 26-ish. So the more negative it is, the brighter it is. And the more positive it is, the dimmer it is. Okay? So I think we left here, and I'll go ahead and highlight a few things. So this is Orion. I probably did this the other day. Orion has a body part, so this is kind of his body part. I guess I should kind of go like this. It looks like an hourglass. That's he's a hunter. And this is his belt, and this is his sword. Okay, if you ever heard of the movie Beetlejuice? Beetlejuice. Okay, so that's the star called Beetlejuice.
Why does it spell like that?
I don't know. A lot of stars actually kind of are Arabic, so I don't think that is. The ones that start with A are mostly Arabic. But which one looks brighter, Beetlejuice or Bellatrix?
Beetlejuice.
Beetlejuice. So which one has the more, closer to a negative number? 0.45 or 1.62? 0.45. 0.45 is closer to a negative number. So the closer something is to a negative number, the brighter it is. See how that works? Just comparing these two up here. What about Sirius? What's its magnitude?
Looks like.
Yeah. It's like a negative 1.44.
That's like really bright.
Yeah, so that's really bright. Actually, the star's name Sirius and the constellation's name is Canis Major. What's Canis stand for? K9, Canis? What's K9? Yeah. So actually this is the hunter's dog. So this is his head, and this is, I think, his kind of legs. You can almost see that one. So Sirius is the brightest star in our sky. Sirius is a good one to pick on. I think we're going to see Sirius here in a new light. The last slide coming up, no pun intended. Even though it's bright, here's the problem. It could be bright for one of two reasons. It could be bright because it's really putting out the energy, or it could be bright because it's just really close to us, right? So kind of the proximity thing. If something's closer, it's going to appear brighter.
So when our sun gets when it starts expanding, is it going to get brighter too, or not?
Yes, yes.
So could it be doing that as well, like expanding?
Yeah, that's true. Yeah, our sun's going to become brighter because it's going to have more surface area. It's going to become orange. If you're somewhere else and have an orange or red appearance, it's going to get brighter because it has more surface area.
So it could be doing that too.
It could be doing that, exactly. So in a minute, actually, I'm going to kind of tell you how we remove the mystery of distance, okay? So anyway, this kind of shows you a car, you know, should you be afraid? Oh my gosh, should you be afraid of cars? Yes, because my husband's telling me that there was like a whole family of 3 kids got hit when they were like going out to their bus recently. And they didn't make it, you know? So anyway, should you be afraid? Well, it depends on height. If it's car light, we know that the car is close to us if the lights are bright. We know that the car is far away from us if the lights are dim, okay? So we just know that, okay? With the distant car, and we're going to see it on a figure here in a minute. We saw a figure when we met last time. With a distant car, the reason it's dim is because the light is diluted. It basically goes in all directions. It's diluted, okay? This is kind of showing the dilution. I think I showed this. I feel like I showed this the other day, where actually this shaft of light is going to hit this sphere, and we're going to have one little box. It goes another distance. We'll call that 2 times the first distance, and it has how many boxes are there? 4. Yep. So we want 1 box, 4 boxes. It goes one more distance. How many boxes are there? 9. Yeah, I almost said 16. 9. Very good. There are 9. See, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9. So that's kind of the dilution of light. That's how that works. That one shaft of light, depending on how far it is.
I had did the homework on this already, because I saw the other.
Yeah, I saw that. I gave you 11. Do you read that about this?
Yeah. Hey, chill out. That's why I understand now. I mean, the magnitude, it made me understand it more. Because at first I was lost, but then I get it now. Like when it's negative, it's going brighter.
Right. When it's negative, it's brighter. When it's positive, it's dimmer. So this is how this works. It's called the inverse square law. Inverse in looking at how things affect each other. Inverse just means opposite. We have a lot of inverse things. Inverse just means as this goes up, this goes down. That's inverse. Up, up, down. So what do we mean by up, down? We mean like if you get farther away, the distance is farther away, the brightness is down. The brightness of when it finally gets to you. So inverse relationship. The squared part, you can see where actually we square the distance. So brightness is affected by distance with distance in the bottom. Now one more thing, actually the very first slide, you can flip back if you have your notes, but I'll go ahead and tell you what luminosity means. Luminosity, we said on the first slide here, means if you could visit that star, it's how much energy it's putting out. So luminosity is visiting the star, and actually it's measured in watts. Visiting the star, and like we have different wattage light bulbs, seeing how much energy it's putting out per second. So this is how much energy it's putting out per second, and brightness is how we see it. So brightness is, this is how we see it. How we see it. All right. One, I can't read my own writing there. Well, one of the things about an equation like that is I've taken all the math out of this class, but sometimes I put this on my unit exams. By the way, I hand out those PowerPoint slides for your benefit. So honestly, every time you come to this class, you should be bringing your PowerPoint slides in. And if I say it's going to be on the test, put a little thing next to it saying it's going to be on the test. So that's why I'm printing those off, just I'm trying something new with Unit 3. So this might be on the test. We can rearrange this, and if you're a math person, you kind of know what that would look like. We can say that how much energy it's pumping out is equal to how bright it looks to us times 4 pi, the distance it is from us squared. We can do one more thing, and this is the coolest right here. Actually, wouldn't you want to know how far away a star is? So we can figure out the distance to a star. How would you do that? Well, there's different ways to do that. Distance to a star. All we got to do is see how much energy it's pumping out. I'll put E for energy pumping out. Pumping out. And we divide it by brightness. That's what we see. Energy it's pumping out divided brightness that we see. And that's one of the few ways we can know how far it is to a star. Why would we want to know? Well, in case we want to leave our own star, you know? So millions of years ago, your great-great-great-great-great-great-great-great-grandchildren gonna have to find a different home. Okay.
Yeah, I believe it.
Yeah.
Think they'll probably move to a moon.
Will they move to the moon? That's not far enough.
I'm talking about like the moons that that have.
Oh yeah, I think they might move to the moon around another planet.
Yeah, that's what I'm saying.
Yeah, that's a possibility. I buy that.
See, I was watching this video, and it was like 10 places we could live, but wouldn't be habitable enough right now. There was this one planet. It was the exact same size as Earth, the exact same gravity, but the wind there, because it was really close to the star, it was the first planet to the star that they had.
The solar wind.
So the solar wind made the planet super windy, and the wind there was 400 miles per hour all the time.
Oops. I don't know. Interesting though. Maybe we'll have to kind of adapt to strong winds like that. That's a good question. So one last thing then, and I almost wish I'd spend a little more time on this, but it'll be a player later when we talk about stars. So don't blame me. So the variable means what letter we use for the brightness something looks like is the letter M, lowercase m, a little m. What we've been talking about, what we call the apparent brightness, what it looks like is the little m. There's a big M out there, okay? And that's called the absolute magnitude. So we have apparent magnitude or brightness, what it looks like. Then we have the absolute magnitude, a big M. The difference now with absolute magnitude is you go ahead and visit the star and you know, you basically remove the effect of distance. So absolute magnitude is kind of weird. You basically, what's LY stand for in astronomy?
Light years.
Right, light years, yeah. Absolute magnitude is kind of a funky thing. We're here on Earth, we basically relocate objects at the same starting line. That starting line is 3.26 light years away. So we line them up and then we look at them again. We say, how bright are you now? And that's the absolute magnitude because we've removed the different distances. We've removed the effective distance. So that's absolute magnitude. So in other words, if we take the sun, which is what we say, minus 26, the sun's very bright. What it looks like is a magnitude of negative 26. That's way bright. If we were to take the sun, and I don't recommend it, but relocate it about 3.26 light years away, which is 10 parsecs, that would be a lot dimmer. It would look like, what's this say, plus 4.9? Kind of almost at the edge of naked eye looking at it. Okay. So I have a slide coming up here, but luminosity, do you guys see? It's important. We've talked about it a few times. We talked about Wednesday, I'm talking about it now. Luminosity is like your light bulb. Luminosity is you visit the star and you're like, dude, how much energy are you putting out? That's your wattage. Luminosity is wattage. So, bottom line, if we go ahead and have the same playing field, absolute magnitude, we can relate that directly to their wattage. Why? Because they're all the same distance. That's how that works. So one last slide, you guys don't actually have this, but here's some apparent magnitudes, and this is where I feel apologetic. The variable for apparent magnitude, what it looks like, is the lowercase m. The variable for absolute magnitude is an uppercase M. So here we have, this is actually what we just talked about a minute ago. How bright does the sun appear? Negative 26. If you move it farther away, 3.26 light years, it's going to appear 4.8. So that's its absolute magnitude. Sirius, that bright star, it goes from a negative 1.44 to just a 1.41. Check this out. Betelgeuse, it's kind of spelled differently there, isn't it? Betelgeuse, that bright star in Orion. Notice that if we were to move it, what does that mean then? It looks like it's 0.45, which is pretty bright. But if we relocate it, it gets brighter.
It's really far away from us.
That means it's farther than 4.26 light years, exactly. So in that case, we're relocating it closer. Same playing field. So what does it mean by this guy if they're the same?
He's at the absolute magnitude for it.
They're the same. It must be 10 parsecs. It must be 3.26 light years away. If you relocate it, it's got the same. Like, dude, you must already be there. So that's how that works. Okay. So let's check out that video I brought.